And hello everyone, I'm Jay. I'm glad to be here to share internal designs of TiDB on Percona Live. Today I'm going to talk about how does geo-replication work in TiDB. First, let me introduce myself. I'm Jay from PinCap. I focus on distributed system, and I love open source. I'm one of the TiDB maintainers. And TiDB is a Kiwi database and CSS graduated project. Also, I love Rust and wrote several libraries in Rust. I'm going to introduce the geo-replication by 3 steps. First is a higher architecture of TiDB, and then a dive into its replication mechanism. And finally, several deployment cases that explain how those designs work in practice. So, what is TiDB? TiDB is an open source NewSQL database that supports hybrid transactional and analytical processing workloads, aka HTAP. It is MySQL compatible and features horizontal scalability, strong consistency, and high availability. Here listed some key features of TiDB. It supports elastic scaling out, which is transparent to applications. TiDB does the shardings for you automatically. It uses two-phase commit and Raft algorithm to achieve high availability and strong consistency. It speaks MySQL dialect. This is the whole picture of TiDB. There are a lot of components here, but don't worry, today we focus on the central part. That is where the replication takes place. Here is a simplified architecture. The core components of TiDB are PD and TiDB servers and TiDB servers. TiDB is a Kiwi database, as I just mentioned, and stores all the data. It automatically splits the data into small shards and reports the metadata of the shards to PD. PD maintains the route table of each data shards and other necessary metadata. It also moves shards around to achieve load balance. TiDB servers are stateless. They pass queries from the client and transform it into Kiwi operations. They communicate with each other using gRPC. Before introducing the replication, let me explain how data is organized. TiDB assigns each table and each row an implicit number and combines the table number and the row number into a unique key. The row content is the value. So the data of a table is sorted in dictionary order, and each table doesn't overlap with each other. The Kiwi pairs are stored in local RoastDB instance of TiKiwi. TiKiwi will divide the whole key space into several continuous logical ranges. We call those ranges as regions. Region is a bunch of Kiwi pairs or split. Don't get confused with the other geo concepts. It's more similar with the region from HBase. The default size of a region is 96 megabytes. You can change it if necessary. We choose the small value to get more accurate balance. The start key and end key describes the range of a region. And all region doesn't overlap with each other. All regions within a TiDB are stored in the same RoastDB instance. A region is managed by a Raft group. Region can have replicas. By default, there are 3 replicas for a region. Here is an example layout of how data are organized. Key space are divided into several regions, and replicas for a region are replicated to different nodes. Now we have an impression how data are organized, but how does the replication work? We just mentioned a region is managed by a Raft group. So we also use Raft algorithm to do replication. If you don't know the details of Raft algorithm, it's okay. Raft is simple, and we don't need to know all the details to understand the replication in TiDB. I will introduce the key points of Raft to you. In a region, all replicas can have different roles. Most of the time, possible roles are leader, follower, and learner. A follower receives the majority votes from other followers, becomes leader. A leader is responsible to handle replications and provide latest view of its data to the clients. It also reports to PD for the configuration of the region periodically. Leader will also send habits to followers to ensure its leadership. If a follower didn't receive habits in a given time, it will start campaign. So if a leader crashes, a new leader can be elected in time. When TiDB servers want to write data to a region, it will query PD for the metadata of the region first. So it will know how many replicas are available in the region and who is the leader of the region. It then sends the request to the leader. Leader will serialize the request into logs and replicates the logs to followers. If leader knows majority replicas have persistent logs to the disk, it will apply the log and return successful response to TiDB servers. The leader also replicates logs to learners, but leader won't count learner into majority. So learner can have almost the same data as the followers at any time point, but it won't slow down the leader's replication. It makes them very quick to be promoted as a healthy follower. This is very important for supporting dynamic configuration changes. When TiDB wants to read some data from a region, it will also query PD for available replicas first. Although I don't draw the PD cluster here. All replicas can serve reads. If leader receives a read request, it will read immediately if it's still leader. As I mentioned in the last page, writes are always sent to leader first, so leader always have the latest data. Read immediately is safe. But if leader cannot ensure it's still leader, it will broadcast habits to followers until the majority follower responds to the habits. The read request will have to wait on leader. If follower receives the read request from TiDB, it will because follower doesn't know what's the latest data, so they will ask leader what's the current log index first, and leader sends back the latest log index, and follower or learner have applied to the given index, they will start serving the request. To achieve load balance, we also need to move replicas around. So we support dynamic configuration changes. There are two approaches to do configuration changes. The first one is simple change. In simple change, we can do one change at a time. Changes are served as a special write. So the changes need to be accepted by majority replicas. The right picture is an example to show how this works. PD finds that a follower in AC2 is overloaded, so it decides to move the follower from AC2 to AC3. It will first ask leader to add a learner in AC3 first. After leader has replicates enough loss to the learner, it will ask leader to promote it into follower. In this time, there are 4 replicas in the region. And finally, PD will ask the leader to remove the replica from AC2. In this step, the configuration is changed from AC0, AC1, AC2 to AC0, AC1, and AC3. The replica in AC2 is moved to AC3 successfully. Simple change is very easy to implement, and each step is executed very quickly. However, simple change can lead to unavailability. Let's consider this case. PD wants to move the replica from one TiDB instance to another TiDB instance, and both instances are in the same AC. Let's say it's AC2. As I described in the last page, when using simple change, there will be a state that there are 4 replicas in the region. 2 of them are in AC2. If AC2 is unavailable, then there are only two replicas alive in the region. Remember that a region requires majority to serve writes and reads, so the region will also become unavailable. To solve the problem, we need joint consensus. In joint consensus, the region will enter joint state first, and when trying to have configuration changes. In the joint state, the new configuration and the old configuration work. Take the same case as an example. The remove replica and the new added replica are in different configuration. So there are 3 replicas in both configurations in all time. Even AC2 is unavailable. The replica from AC0 and AC1 still alive. So in both configurations, the majority replicas are alive. Then the region can still serve requests. Joint consensus is complicated but safer. All I have introduced are provided directly by Raft algorithm, but commit group is something beyond that. We have taught that Raft ensures that writes are replicated to majority before they are considered committed. But sometimes majority is not enough. For example, if we have 2 ACs and 3 replicas, there will be an AC has at least 2 replicas. Let's consider it as AC0. The AC0 can form the majority by itself. So the other AC may not have the latest data. If AC0 crash, then the majority of the region is crashed. Then the latest data is lost forever. The commit group is designed to solve the problem. We consider each AC as a group and assign replicas to the groups. We add extra constraints on how logs are committed. The first one is the old rule that the logs should be considered committed only after they have been replicated to the majority replicas in the configuration. And the second is new. All the logs have to be replicated to at least 2 groups before they are committed. So even AC0 is failed, we can still ensure that there will be at least 1 replica in the other AC contains the latest data. The number 2 here hard-coded at the moment because we think true AC failure hardly happen. Commit group has another usage that allows follower replication. We assign a follower in a group as a delegate. If you process the logs from the leader and send it to the followers in the same group, take 5 replicas as an example. Delegates can reduce the bandwidth between ACs by half because the leader doesn't have to replicate logs to the other followers when there is a delegate. We have mentioned a lot of how PD removes replicas around, but how does PD make decisions? PD schedule replicas using placement rules. The rules can constrain the number of replicas, and it also can constrain the rough rules, like which replica should become leader. And it will also control the geolocation, decides where to place the replicas. The rules take effect within ranges. The range can cover one or several regions. When PD wants to make a decisions to a region, it will query the rule database about what rules should be considered, and it will generate a decision that best matches all the rules. For example, as shown in the graph, we can configure a rule to allocate 5 replicas for the metadata, as those data is small but quite important for the cluster, and all the other tables remain free replicas. That's all for the details of replication implementations. And now I will introduce several deployment cases to explain how these implementations guarantee consistency and safety. First is the classical free ACs. In this case, all replicas and leaders are distributed among free ACs evenly. As we mentioned before, Raft guarantees majority safety. So even there is a AC down, the other 2 ACs can still form the majority and provide service. No data is lost. The disadvantage is all the data has to be replicated to at least 2 ACs. This is the price of data safety. And rewrite performance can also suffer if the leader TiDB server requested is not in the same AC of the TiDB servers, because TiDB servers have to send the request across ACs. This can be optimized by add placement rules in PD. Placement rules can require PD to schedule replicas and leaders to the specified ACs and nodes. For example, if we know that a table or a part of a table is accessed more frequently in an AC, we can schedule the leader of those regions to the AC. In such a way, we can reduce the replication across ACs between TiDB and TiKV. If the table can be accessed in multiple ACs, the placement rules will not bring much improvements, but we can also optimize the read request by using follow reads. Although follower will still need to send an RTC to leader to ask for the index, but read index is much cheaper than read keys. Free ACs tolerate one down AC out of box. However, it's expensive because the AC is more expensive than replicas. especially for the private cloud. So another common deployment case is two ACs. When using two ACs and still want to prevent data loss when one AC fails, in the classical way, it's recommended to use even number of replicas, for example, 4 or 2. But when choosing 2, the region will become unavailable even one replica is unavailable. So we usually choose 4. When using 4 replicas, all the data majority replicas must exist in both ACs. So either AC down won't lose data. But when either AC is down, the majority is unavailable anymore. So the region is also unavailable. This approach is expensive because back in the 3 ACs deployment, we only need 3 replicas to tolerate one unavailable node. But in 2 ACs, we require 4. Can we achieve both data safety and high availability in 2 ACs case with lower cost? The answer is definitely yes. With group commit, we can achieve both. We can use 3 replicas and also enable group commit. As we have mentioned before, group commit ensures only data written into 2 ACs are considered committed. So either EC is destroyed, the other will still contain the latest data. Data safety is guaranteed. And we usually choose one AC to be a primary AC and the other one is secondary AC. Primary ACs has more replicas. And comparing to the even number of replicas, in this case, if secondary AC fail, the primary AC can still contain the majority of replicas. So we can still make the cluster recover by removing the group commit. After that, the second AC will not be guaranteed to have the latest data. Does it sound like asynchronous replication in the master-slave deployment in the traditional database? Indeed, we follow the concept implemented in our way. This is the graph to show the state transitions. The state is managed by PD. At first, the cluster is in sync state. In this state, group commit is enabled, and data safety is guaranteed from failure of either AC. If secondary AC fails, PD will wait for its recovery for a configured time. If timeouts, PD asks all regions to disable group commit. The state becomes asynchronous. In this state, data is guaranteed to only replicate to majority replicas. Because primary is still alive, it can serve requests again. After some time, the secondary AC is recovered, and PD will ask all regions to enable group commit again. PD can set the state back to sync immediately because we guarantee data safety in sync state, but secondary state may not have enough data yet. So the cluster state is in sync recover. When all the regions have replicated the latest data to the secondary, PD transits the state back to sync again. In this talk, I introduced the GEO replication mechanism in TiDB. It uses Raft algorithm to ensure atomicity and consistency. We use placement rules to reduce latency and bandwidth in multiple AC situations. We also introduced group commit to ensure safety across even number of ACs. We also use follow read and follow replication to reduce cross AC bandwidth. And if you have any other questions, you can ask me here or in the Twitter pin cap, or just add me BCJ. That's all. Thank you.
Awesome. Thank you, Jay. I've got looks like a few minutes for questions. So I'll throw one out there right away for you. I think there is another role candidate in the Raft algorithm. Is it missed in your slides?
Yes, indeed. Generally, a follower will become candidate first to start campaign. But the candidate role is not very relevant to the replication. So I omit it on purpose so that we can focus on the general replication mechanism.
Cool, thank you. And then one more. Is it possible to achieve high availability for just some of the tables instead of the whole database?
Yes. As I just mentioned in the placement rules, it's totally possible to configure different placement rules for different tables. And the placement rules operates on ranges. And if you just want to like configure the table 0, 1 to have 2 runners, and the table 2 has another followers, they will not be conflict with each other. And they can both operate, and they can both take effects in the placement rules.
Awesome. Let me check. It does not look like we have any questions in Slack at this time. So with that, I'll say thank you, Jay, for that talk. That was really interesting. And
okay, thank you, Mike.